let's design Discord or any type of group chat application, something like Slack, which you might be more familiar with, or even Microsoft Teams. But the main background with an application like this is that we have certain types of groups. I think Slack calls them workspaces, but in general, you have one kind of entity that is a group, and people have to be members of a group to actually see any types of messages in those groups. And you've probably used an app like this, but I think the easiest way to explain it is to just show you. So this is my Discord server, or a Slack group or a Microsoft Teams group, and each server has a bunch of channels. So this is like the welcome channel, and right now you can see we are in the coding help channel. This is an individual channel, and then each individual channel will have a history of messages. Of course, like any chat app, these are going to be ordered based on time, with the most recent messages showing up at the bottom. But you can see that Discord and many other chat apps have kind of this functionality. When we actually open up this channel, we're not going to immediately go at the bottom, because there could be a bunch of messages that we haven't seen, and we want to keep track of those messages that we haven't seen so that we can pick up where we left off. And also with chat messages, users can mention each other, like with the @ symbol, and you can type in somebody's username. And when you do that, typically in the channel name, there is like a notification which shows like 3 unread messages, not unread messages, but 3 mentions that are unread. And this is kind of what that notification symbol would look like. The number of notifications could apply to direct messages, which Discord also supports and most chat apps support. So direct messaging, like DMing, I think most people are pretty familiar with that. It's similar to like any text messaging type of app. But keep in mind that this number of notifications could apply to like a Discord server or like a Slack workspace, but it could also apply to an individual channel in that particular server or workspace. So now let's get into the functional requirements. With all the functionality of Discord, what exactly are we going to be focusing on? Let's say we actually want to focus on the servers and the channels within those servers, and then sending and receiving messages in those channels and being able to pick up where we left off. If we didn't have to implement picking up where we left off, it would probably be a bit simpler. So with this design, we're going to be going a bit deeper into this functionality and not kind of focusing on the generic like DMing people functionality. So we want users to be able to join servers and channels, but we won't be focusing on that either, because sometimes you need like an invite to join a server. Sometimes some channels have like permissions, like you don't have permission for a particular channel. And also with Discord, you can call people and video chat. We won't be focusing on that either. So we mainly care about the chat functionality within channels. We want to be able to pick up where we left off, and we also want to be able to have a visual indicator for like the number of notifications for a particular channel and a particular server. So without actually opening that, if we have a bunch of mentions, like somebody has explicitly mentioned us in a server, we want to be able to have a count for that, and the same thing for a channel. We as users can send messages in the channel and see them in real time. So that's another thing. Of course, on page load, we should see the history of unread messages. If there are no unread messages, we should start basically, at the most recent message. But even beyond that, as messages are coming in real time, we should see those with as minimal latency as possible, because that's the whole point of chatting. And it's not like, in this case, let's say we don't have to worry about images and videos, we just care about the actual like text. So with that, it should be feasible for us to get this to as low latency as possible, which kind of brings us to the non-functional requirements. What we actually care about with these servers is that the latency is minimized. And in terms of availability, of course, we want to have as high availability as possible, but we could have 100% availability. And if we have high latency, it doesn't really matter. I mean, if we have to wait like 60 seconds after a message is sent to see it, then we can't really chat in real time. I mean, that's even worse than like a phone call. Sometimes in a phone call, you have like a 1-second lag or something, but we really don't want that with text communication. So we favor lower latency, but at the same time, we want to build our design so that it's redundant and fault tolerant and also highly available. And let's say we're actually a startup, like we're designing Discord as like startup engineers, and we don't necessarily have a massive amount of users, but we also want to be able to handle scale, but we care obviously most about low latency. So let's say we're actually supporting 5 million daily active users. Maybe we're in the early days of Discord, and we might have, let's say, 50 million messages sent per day. But do we really care about the total amount? We care about where we're going to reach the bottleneck. So when it comes to these non-functional requirements, I think it's important to dig deep into what the limit could be. So in the context of Discord, how many people could be in a server? What's the max number? Let's say it's something like 20,000 is the limit of people in a Discord server. And this is actually pretty realistic in the early days of Discord when they didn't have to run into many scaling issues. And as their user base growed, certain servers were reaching more users, then they had to kind of rework their design. So a server could have up to 20,000 users. Let's say there's 200,000 messages sent per day in a server. Now, most users in a server aren't going to be active most of the time. So let's say we're actually dealing with the same number of messages per day in that server. In the worst case, all these messages could be in the same channel. That would probably put some strain on our resources, but on average, let's say it's actually even less than that, maybe 10K messages per channel in a single day. So that's a high number, but at the same time, it's nothing super crazy, especially because each message is going to be text-based. Let's say the max limit for a message is going to be something like 2,000 bytes, so 2,000 characters most likely, but there could be some additional metadata with that. So this is going to be 2 kilobytes per message, and we could, continue these calculations and get to the exact throughput of data that we're expecting, but I don't think we really have to. At this point, we kind of get that we'll have a large amount of data, but it should be a reasonable amount. And what's probably more important is the observation that in Discord, most of these messages sure are going to be written. Most of these messages are not going to be read very frequently. We're actually only going to be reading the most recent messages. So you might want to look at all the messages in the last day, which could be something like 10,000, but even that is the upper bound. Most likely it would be much less than that. It might be closer to 100 messages in a day. With that, I think we have a few considerations with how we can implement our design. So now moving on to the high level design. So before we get into the actual architecture, let's kind of understand what types of actions that we're actually going to be supporting. So when we have send message, of course you have the body of that message, and like the ID of that message will be created server side. And of course each message is associated with a particular Discord server in a particular channel. Now sending a message is straightforward. That could be sent in a typical HTTP request. But when it comes to receiving messages in real time, like as soon as somebody sends this, I want to, as a user, if I'm in the same channel, I want to see that message as soon as possible. How would I implement that? We can technically do it with HTTP. We can do polling, like maybe every few seconds we can check, is there a new message, by sending an HTTP request, reading from some database, and then we'd see, okay, a few new messages that we haven't seen already, so we can fetch them. Now, what would the interval of this be? Every 1 second? That would mean in the worst case we have to wait 1 second after a message is sent before seeing it. That's not too bad. It might be acceptable, but the problem is that there probably isn't going to be a new message every 1 second. So this is not going to be very efficient in terms of resources. We're going to be getting, for every person that's in the channel who's active at a particular time, we're going to be getting a request sent from them every 1 second. That's a lot of traffic in the worst case. So this is not very efficient. I mean, we could slow this down maybe every 5 seconds. We'd still be sending a lot of requests, and in that case, we'd be increasing the latency. So a better approach to HTTP, well, at least HTTP 1, would be WebSockets. Now, actually, HTTP supports the similar functionality of WebSockets nowadays, but I think a lot of interviewers aren't aware of that, so I prefer to kind of focus on WebSockets. Now, if you are familiar with HTTP streaming, I think it would be a good opportunity to kind of demonstrate your domain knowledge, but who knows, maybe if you get an interviewer who isn't familiar with it, they want you to still be familiar with WebSockets. Now, at a high level, with WebSockets, we do not have to implement polling. The server can actually push new messages immediately as they are sent in a channel to every user who is in that channel, who's active in that channel, if they have an active WebSocket connection with the server. So at a high level, this will help us reduce latency. As new messages are sent, we should be able to see them relatively quickly. Now, this kind of covers the case of real-time messages, but what about opening up a channel and seeing all the previous unread messages, or just starting at the most recent message? How do we handle like the page load? So at a high level, the user could make a request to like view the channel, and by doing that, they would get a response of the messages. Not all the messages, of course. We could probably paginate this with like a page token. So assuming that the user is up to date in that channel, they would just start maybe at the last like 10 messages that were sent, and they view them like in chronological order. And of course they could scroll up, which then they would get 10 more messages up there, and etc., etc. Most likely though, people aren't going to be scrolling like all the way up. They care about the most recent messages. But of course, if someone has unread messages, so they start here, they have 10 messages here, but they have 50 unread unread messages down there. The interesting thing is that this experience viewing a channel is going to be different for every single user depending on what was the last message that they read or what was the timestamp of the last message that they read. So when we talk about, making a request to view the channel, of course we're going to be retrieving information from a database, but now we kind of know what we're looking to optimize. We know that the time range of all these messages is going to matter, but we probably don't need to query every single message because we only care about messages in a single channel. We're only going to be looking at one channel at a time. And let's say that on page load, like before you even view a channel, you do have some type of visual indicator, like maybe 3 or more mentions in that channel. So that should actually happen on page load. So this should be a relatively quick thing to do, to be able to calculate how many messages in that database for every single channel were actually mentioning me. So now while our high level design is pretty simple, and we could actually throw in another server over here, which is to indicate that this is going to be actually the WebSocket server, which is going to be pushing new messages to the client immediately, whereas maybe this will be HTTP based to like retrieve channel messages and like notification counts. And you can actually have WebSocket endpoints on HTTP servers. I'll leave it like this just to have it simplified, because now we're going to start looking at the details and we're really going to be focusing on the database design. We have many approaches we could take. I'm going to be focusing on if we did this with SQL, because as we kind of mentioned earlier, we're not going to be dealing with a super massive scale, and we do have a pretty obvious strategy for starting our data. We can use the channel ID, but I'll also discuss how we could do things with like a non-relational database, something like MongoDB, which is actually what Discord was originally using, and eventually they migrated to another NoSQL database called Cassandra, which gave them a lot of flexibility on how they wanted to partition their data, and we'll briefly discuss that as well. So a couple of the most important tables we could store in our database is of course the messages. This is going to be the largest table. The important fields we'll be storing is, of course, we'll have an ID to identify every message, but we mainly care about like which user sent that message. Did they mention anybody? Because we do need a way to count how many times a user was mentioned. And of course, every message has to be sent in a server, so we need the server ID, and in a channel, so we need the channel ID, and it has some time associated with it. This time is going to be very helpful for us ordering our messages. So we probably want to index the messages based on the sent at time. But remember that messages are only viewed in a single channel, so it might be better to index based on the channel ID. What might be even more important is with the massive size that this table is going to be, millions and billions of messages over like the course of a week or a month, we probably need to break this up. We can implement sharding. The best way to do this is probably based on the channel ID, so that every time a user makes a request to view all the messages in a channel, they should be able to hit a single database shard. They don't have to look at multiple shards. And it's not the end of the world if a second channel in the same server actually has messages on a separate shard, because then when the user wants to view that channel, they can hit a different shard. It doesn't really make a difference. So we definitely prefer to shard based on channel ID rather than server ID, even though server ID would probably be pretty good as well, because doing it that way kind of guarantees that all the messages in a channel are on the same database shard. So with this type of sharding, we can then index based on the date, because we already broke our data up into shards, so we shouldn't have a massive amount of data on every shard, and we know that all messages for a channel ID are going to be on the same shard, so then we can kind of afford to index based on the date, because remember, we only care about the most recent messages. So ordering based on date is going to be important. That's going to speed up our queries. Another thing we could do to speed that up is to also add a caching layer in between. Some channels, of course, are going to have a lot of requests made to them, and to speed those up, we can have that caching layer, but at the same time, this caching layer is going to be updated very frequently, because as users send messages, the cache will get stale pretty quickly. We could discuss a bit more in depth on what happens when a user actually sends a message. Do we also want to update our cache at the exact same time? But I think that's not the main concern at this point. With the way we've designed our database, querying the most recent messages should not take super long, because we're not dealing with a super high amount of users per each server and each channel. What's more important, I think, at this point is to discuss how we'd actually implement the functionality of when a user has not seen like the last 50 plus messages, they want to pick up where they left off. And so that's why we have a second table for user activity. So for every single user, we're going to store for every channel that they've already visited, what was the last time that they visited that channel. Because if we store this information for every user, then it's possible for us to make a query on the messages table to show them all the unread messages. An example query for that could look something like this. where we have a subquery. So for a particular user like myself, like NeetCode, we want to know what was the last read activity from user activity, and we could have specify here for me. So that would give us all clearly this is feasible for a relatively small scale. And remember that these messages would actually be paginated, so it's possible we'd have a limit statement down here to limit the number maybe last read, then upper or a single was mentioned. So that is going to be slower, take a few extra seconds from disk. But still, what would we do to store those notification counts on the cache? Because reading the notification count should be quick. So maybe the key could be now. How are we actually going to calculate that notification of and then now I do want to briefly discuss how Discord actually handled this. I don't believe they actually time the systems, but in general index much slower. So that would be the dynamic document. Cassandra is distributed. It is kind of sharded. It has multiple partitions where some data will live on one partition and the rest of the data might live on another partition. And there's one key called the partition key, which will tell you where that data is stored. Now, what do you think Discord shows as their partition key for messages? It was the channel ID. So all messages for a channel should be on the same partition after key. Time they actually did not go with a sort to run queries that is handling a mapping from R, because even the things that we kind of now, compared to Netflix, YouTube is a bit different in that users can actually upload videos, and it's actually free as well. Pretty much anyone can upload videos. And of course, if we can upload videos, we can also choose to watch videos as users. And when it comes to YouTube, this is actually the core functionality, though that doesn't mean it's simple to implement. There's a ton of complexity with reaching the scale that YouTube does with even just these two features, but this is actually not all that YouTube is capable of doing. There's a lot of data. You can obviously search for videos. You can obviously have videos recommended, and designing that recommendation system could be its own design problem, but even then it would not be able to be fully described and designed in a 45-minute interview, of course. And users can, of course, comment and interact with videos by liking or disliking them, and there's a ton of probably analytics that goes on with reporting views, and I'm sure there's like bot prevention with like comments, even though there's a ton of bots in the comments lately, and advertising, and the list could go on and on. The point I'm trying to make is that when it comes to an ambiguous kind of design proposal like this, there's many different directions we could go in, and of course we can't explore all of them. So then moving on to the functional requirements, let's say that the main features that we want to focus on are going to be uploading videos from a user's perspective and then watching videos from a user's perspective. So these are the two main functional requirements we want to focus on. If we have time at the end, maybe we can kind of explore how we can extend our design to handle additional functionality, but these are the main things that we want to be able to focus on. When it comes to non-functional requirements, a first one that comes to mind is reliability when it comes to videos. You would never want to run into an issue where somebody uploads a video and then that video is somehow corrupted or deleted. We definitely don't expect that when we're storing something on YouTube. Even though it's free, we wouldn't want a video to just disappear. So we really need the videos to be extremely reliable, at least in terms of storage. And talking about the scale that we're going to be handling, even a single video can have potentially thousands of concurrent viewers. So that's what we have to kind of keep in mind. Of course, we're going to have a ton of users. Let's assume that we're designing YouTube to handle 1 billion daily active users, which is about accurate, I think. Now, when it comes to these users, let's say that each user is watching 5 videos per day, but the upload ratio is going to be 100 users are watching videos for every 1 user uploading a video, or this is the ratio of reads versus writes for videos. So if we have 5 users watching a video per day, we have 5 billion of videos being watched per day. If the ratio is 100 to 1, that means 1% of 5 billion is going to be the number of videos uploaded per day. So that is going to be 50 million videos uploaded per day. So a massive amount of throughput. Now the good thing is, among these 50 million videos, most of them probably aren't going to be getting a ton of views. If I had to guess, I bet the top 5% of videos account for like 90% of the views. But this is just off the top of my head, but I think we can kind of design this in a way that we assume that most videos will not be getting views, though they do still have to be stored, and we can't let them get deleted. Now in most cases, doing a bunch of complex math isn't super important. It's about coming to the right conclusions, which we kind of are. We also have to keep in mind that when it comes to availability, we definitely want to favor availability over consistency. What do I mean by that? Well, every time you go on YouTube and you refresh the YouTube homepage and you want to see like a bunch of videos on your homepage, every time you make that request, every time you refresh, you should get a correct response. You should get an HTTP 200 response and things should load. And it's okay if we have to sacrifice consistency to achieve that. What do I mean by that? Well, what if you're in your subscription feed and somebody just uploaded a new video? Somebody you're subscribed to just uploaded a new video 1 second ago, and you just refreshed your homepage. You see a bunch of videos in your subscription feed, but none of them appear to be the one that was just uploaded a second ago. Hypothetically, this could happen if we have multiple storage systems, and one of the storage systems that you happen to be reading from when you refreshed the page was this one, but this one did not have the most up-to-date data. This one did not have the new video uploaded, but this one did. But eventually that video will be replicated to the other storage, but it just takes a few seconds. So you're getting stale data. Our data storage is not favoring consistency, it's favoring availability. And the worst thing that would happen in this case is most likely you would have to wait a little bit longer. Maybe when a new video is uploaded, you have to wait 5 seconds before you can actually see it, or maybe in the worst case, something like 10 seconds. But is that really that big of a deal? I think it would be a lot worse if you refresh the page and it didn't return anything to you at all. And lastly, we want to obviously minimize the latency as much as possible. When you click to watch a video, ideally it should start playing immediately, even if the entire video isn't loaded. And if we have a good internet connection, we shouldn't have to experience any buffering or waiting for the video to load. Now let's start with the high-level design. And I'm going to start with the user journey of uploading a video, because uploading is probably going to be more complicated than actually watching a video. And this will probably give us a better sense of the infrastructure that's going to be involved with our design. Now, since we're dealing with such a massive scale, 50 million uploads per day, we probably can't handle that with a single server. So we would most likely have a load balancer sitting in between a bunch of application servers so that we can kind of scale this horizontally. Now, this is a pretty generic thing. For now, let's just assume that how we kind of do this doesn't really matter whether, the user hits this application server or this one. So for now, I'm going to simplify our design and just kind of draw it like the user is making an upload request to the application server, even though under the hood we know it's of course going to need to be load balanced. Now, even the act of uploading a video is not as simple as it might sound. What happens if there's a short internet connection breakage, even for just a second, and we're uploading a file that's over a gigabyte? We were already halfway through, but now would we have to restart over, or could we start where we left off? Let's assume that this is not the direction that we want to go in, and we can just kind of say that once the video is uploaded, it's going to be stored in some object storage. And let's say that this is where we're going to store the raw files that the user uploads. But firstly, the reason we're using an object store is because that's a lot better for storing media and large files like videos. We probably don't need to store that in a relational database, for example. And also object storage, typically, something like AWS S3 or Google Cloud Storage, they kind of handle that replication for us. So we can kind of safely assume that if we store something in an object store, we don't have to worry about it being deleted. And that's generally how cloud file storage works, things like Google metadata associated with every video. Going over what the API for uploading would look like, it would obviously have a title and a description and the actual video content itself, maybe something like an MP4. That's what's going to actually be stored in object storage. And there could be a bunch of other things that we store that the user shows. On YouTube, people are actually creating the videos, the content creators. So every time we want to actually show a video to a user, we're gonna have to join that video with the user information and the video metadata of the video itself, and the person who created it, of course. So long story short, every time we upload, because we're gonna have the object store, in that case, it stores things very flexible. So let's say, one collection is videos. Every video document will have all the information about a single video that we need. And we also have another collection for a user, and all basically, and then relevant, actually at the it's gonna be, YouTube and having them to a object storage to make it enough. This is how we can have these videos are going to be getting static files geographically, like the actual metadata associated with a video from a database, but to actually speed that up, because probably we know that in-memory videos off, most likely newer videos are going to be getting more views, so we can probably have an LRU cache implemented here. So now, finally, let's actually start playing videos uploaded per day. So my question is, how many workers here, assuming that they can actually encode the videos in parallel, which, this is a pretty easy service to scale horizontally, at least at the high level. I'm not saying, video encoding isn't a topic to understand, but assuming that at a high level, one worker can encode one video at a time. So if one person uploads multiple videos, or, if 10 people are uploading videos at the same time, they'll be added to the queue, and then they'll reach the encoding service before they're actually encoded and written to storage. But the point is that multiple videos can be encoded at the same time. There's no dependency or anything anything like that. So if we have 50 million uploads per day, and assuming that every video takes 1 minute to encode, which is probably too small, it would probably take longer than that on average, but let's say, you know, these workers are really, really good, they have really good resources, and maybe most videos that we upload are going to be pretty short. So in terms of capacity planning, how many workers would we need here? Well, 50 million uploads per day, that's assuming 100 seconds in a day. We can divide that by 100,000. I think we get to roughly 500 videos per second are going to be uploaded per day. So, you know, the first thing on your mind would be, well, can we just have 500 workers? No, that's pretty naive, because remember we said that it takes 1 minute to upload or to encode every video on average, let's say. So if we only had 500 workers, and in the first second we have 500 videos uploaded, okay, each of those workers is encoding a single video. Now 1 more second goes by and we have 500 more videos uploaded, but every worker is busy, so we add those 500 to the queue, and then another second goes by and we add 500 more, and you know that this keeps happening until 1 minute has passed, and then finally these 500 are done and we can store them, and now the workers can get 500 more videos, but by this point our queue would be backloaded pretty hard. At this rate we would never get through the backlog, so we need more than 500 workers. If you do the math, there's 60 seconds in a minute, so multiply 500 by 60, you'd get to 30k workers, and this is roughly the answer I personally would be looking for. Now with video encoding, it's probably pretty hard to get an accurate estimate, and I'm not sure if, you know, one worker can actually handle multiple videos at once. Maybe that's the case, but the important thing I would be looking for if I asked you this is that, you know, we definitely need more than 500 workers. We need more than how many videos are going to be uploaded in a second. That's for sure. Now another interesting thing about this problem is actually watching a video. Let's talk about some details on how this can be optimized, and the best way to do so is by looking at an example. So right now I'm on YouTube on my channel specifically. I'm going to go ahead and open up our dev tools, and we're going to be focusing on the network tab. I'm also going to filter this on XHRs, and I'm going to click one of the shorter videos. You'll see why in just a second. So first thing you see here is this is how much of the video has buffered. You can see this portion of the video has buffered. When we watch a YouTube video, we don't need to wait for the entire video to download before we watch it. We're going to be starting at the beginning, presumably. We only need the beginning to be loaded. But watch what happens when I click over here. If I skip to this part of the video, we would, well, it just kind of loaded a little bit. So now I'm going to skip over here. Watch what happens. See, it kind of immediately buffers. So that's what we want to do. We don't need the entire video to be loaded, but it's true that some people might be skipping around. They might skip around to this part, which seems to be popular, and that, you know, this part of the video has not loaded, only this part has. So what's going to happen when I click here? Well, that part got loaded. And what's actually happening here, if we scroll down in the request, the most recent request is a request to actually load that portion of the video. We are not using streaming to do this. We're actually making HTTP requests to load chunks of the video. I'm going to kind of expand this here. You can see a request was made here, and what the response was, it looks like gibberish to us because this is actually, you know, that portion of the video. And going back to the headers, when you scroll down to the response headers, you can see that, okay, actually this was not the video. This content type is audio. So I'm going to hit the second one over here actually, and scrolling down to the header, and then looking at the content type, we see that this one was the video. So actually it looks like the audio is being fetched separately from the video. So this, when we look at the response, is probably the video. Before we were probably looking at the audio, not that it looks any different to us. And I'm going to go ahead and refresh this and do it one more time. So we can see, pausing this, a portion of the video has loaded here. So we're going to scroll down to the requests. We can see the video playback requests are the ones that are actually loading the video itself. And as I click here, new chunk of video was loaded. So let's scroll all the way down to see that one over here, these multiple requests. And you can see that some of them are larger than others. But the point is that 1 megabyte of data is easier to transfer than the entire video, which might be, I don't know, like 20 or 30 megabytes. And this is the technique to lower latency, loading a video via smaller chunks. Now, while rendering and loading videos is also a domain knowledge heavy topic, higher video to the user before they can start watching it, we can just call video streaming, not necessarily live streaming, because we know that video is already stored. It's not like a live feed, but the video is being streamed, meaning it's being sent in small chunks, versus like when you actually download a video, that's not streaming. That's like taking the entire file that's stored and then sending it to your computer and then storing it. Whereas video streaming, I believe those small chunks are actually stored in your computer's memory, which is also why you would not want the entire video to be taking up all of your memory. So most likely there is some client-side code that is handling that and freeing memory, because it's pretty easy to write client-side JavaScript that will crash your browser and take up all your memory. So that's kind of something as a front-end developer you might want to keep in mind. Because if we were watching like a 10-hour long video, which definitely exists on YouTube, we would not need the entire video to be buffered in our memory. We could just skip around the video. But going back to what protocol we might want to use for this, since we want latency to be as low as possible, you might favor at a high level, there's two protocols, UDP and TCP. You might favor UDP for video streaming. Now that's probably a better choice for video live streaming, because as like a sports game is going on, if you miss 1 second of it, you don't want to go back to that 1 second. You want to keep up with the most up-to-date information. So you want to stay what's happening in real time. That's what you would want if you were live streaming something or watching a live stream. That's what UDP favors. But with an actual video, we know that video is stored somewhere and we want to watch the entire video. If you're watching like a movie or something on YouTube, you don't want like to miss 2 seconds of it, because that might be like the actual plot point. So TCP is favored for reliability. That will ensure that we get the entire video. There's not going to be any missing gaps in the video. And sure, it might take longer to do that, but as long as we send it in small chunks, it should be okay. And that's exactly what we saw was happening with YouTube. It was sending HTTP requests, which are built on top of TCP. So I think that is kind of also another important question in the context of YouTube, compared to a lot of like other system design problems. And also there's a lot of other things we could explore with this, especially when it comes to uploading videos, keeping things at a high level. We probably want to rate limit this. We don't want somebody to just be able to upload like an infinite number of videos, or that could be implemented in the load balancer itself, which we kind of like omitted from this design, but we know it does exist. Also, when it comes to recommendations for YouTube videos or even searching, we'd probably want to have other auxiliary services which read from our metadata, and we probably want to store like a history of what types of videos does this person watch, what types of videos do they like, so we can kind of build some recommendation for them. And for searching videos, that could be its own topic. Like that's kind of like designing Google search, because there's a lot of like indexing you can do. You probably do want to incorporate recommendations with searching as well, but also you want to have like the metadata, like the description, the title, how many views does a video have, which videos are most relevant when searching which types of strings. We could have some autocomplete with that, and those most likely would be built on top of this, or those would be built separately from this kind of core functionality. Now, one last thing I wanted to cover, because I think it's always interesting to understand how this type of service was actually built. What YouTube actually did was not use a NoSQL database. They actually used MySQL, which is a relational database management system. Now, you might be wondering, why didn't they use NoSQL? And I definitely don't know the details. One guess I have is that YouTube was actually first created, I think, in like the early 2000s, maybe 2004 or 2005, and MongoDB did not exist at that point, and they probably didn't need to handle the same scale that they do right now. But as time went on, they found that they did need to scale their database. I think what they first did was added read-only replicas, because of course this is a read-heavy system, so reading is going to be more common than actually uploading new videos. But even then they ran into issues, and next they tried to add sharding, and so they sharded their MySQL database, and they ended up having a lot of complex code in their application server which properly routed user requests to the correct shard. I'm not exactly sure which shard key that they used, but that's what they did. And then eventually the long-term solution they found was by building a new engine. It's called Vitesse. I'm actually not sure how it's pronounced, maybe Vitesse, but this was something that was created at YouTube, and this is basically to decouple the application layer from the database layer. The application layer should not have to know about how the database is sharded. So Vitesse was added like as a middle layer in between the application servers and the database, at least at a high level, and that is kind of where all the logic for sharding and routing the requests correctly lives. And this is kind of how they were able to take even a relational database like MySQL and scale it up. Now, maybe if they could go back in time, Vitesse was later open source, and it's actually a very popular project that's still being used. It's very modern, it's very, very powerful. It's being used by new companies like PlanetScale, which are taking MySQL and then adding Vitesse to it and just selling that as a product, and of course adding more functionality. But this kind of shows you when you reach, well, if we're dealing with a lot of read scale to and MySQL and Vitesse in like the Vitesse docs here, and probably other places on the internet. Now let's design Google Drive. To quickly go over the background, with a server you can do a lot more. You can definitely edit files as well. Like if you had a Google Doc stored on your Google Drive, you could definitely edit that file because it's just a regular like text file. You can share files as well with other people and kind of manage the permissions for every file. There's two attributes. Well, we'll talk about S3. Let's say that we have about 200 million total users, which is probably, to be honest, small for Google Drive. There's probably over like 1 billion. But in terms of daily active users, let's say that we have something like 50 million daily active users, and every single user is going to be given 15 gigabytes of free storage, which is exactly what Google Drive offers. Now, of course, there's going to be a subset of the users that actually pay for additional storage. Like some people might be paying for a terabyte of data, or even maybe a petabyte, or maybe even 10 terabytes or 100 terabytes. But since Google Drive is kind of supposed to be a user-friendly product, like for consumers, not for like developers necessarily, probably people aren't going to be storing like petabytes of data on here. And since it's going to be such a small subset of users that are storing more than 15 gigabytes, most likely, we can kind of just assume that the average user is going to have 15 gigabytes. And in addition, most people aren't actually going to be taking up all 15 gigabytes. But then when you get to the total amount of storage that we're going to be taking up with this, remember 50 million is 50 and then 3 zeros and then 3 more zeros. And when you multiply 15 gigabytes by 1,000, we get 15 terabytes. When you multiply that by 1,000 again, we get 15 petabytes. And actually 50 million is actually the daily active users. The total users is probably what we care more about in terms of the total storage. So let me scratch this 50 and replace it with a 200. So we actually have 200 million users. Our math is still the same up until this point though, because we basically multiplied this by 1 million and we got 15 petabytes. Now multiply this by 200 and we will get 1500 plus 1500, which is going to be 3000 petabytes of data, which basically in conclusion is a very, very large amount of data. That's the main conclusion here. Also 15 petabytes is actually 3 exabytes, but I personally just remember the units up to peta, and you can see if you just write it out as 3000, you don't even have to know the units beyond this. But what's also worth mentioning that every file that somebody uploads to their 15 gigabytes of storage, we really cannot allow that data to be deleted. So it's pretty safe to assume that every file that's going to be uploaded is going to need to be replicated, and most likely not just in a single zone, because what if there's a natural disaster and one of the data centers is destroyed for some reason? We probably want to replicate this around the world multiple times, at least 3 times, but maybe even more than that. So basically 3000 petabytes is a lot, but we're probably not able to download. That's really not what we're trying to get out here. This isn't like, say, kind of the read to write ratio is 2 to 1. So there's going to be 2 reads for every write. So every file that's uploaded, let's say there's 2 files per day, 10 megabytes each, there's going to be 4 files that are downloaded, 10 megabytes per each. Now in the context of Google Drive, throughput is probably not the biggest problem here. Even latency isn't necessarily the biggest problem if it takes a couple extra seconds for a file to download. That's really not what we're trying to get out here. This isn't like we're watching YouTube videos where you want to have a really user-friendly experience. What's probably most important in the context of Google Drive is that, first of all, it's always available. You'd never want to try uploading or downloading a file, and it could be a really important file that you're trying to download. You would never want it to not be available to you, because at that point you would probably not even feel safe uploading data to Google Drive. You'd rather just store it on your computer. So availability is probably the biggest, most important requirement here non-functionally, in addition to reliability, because obviously you could upload a file and then one day it's just not there anymore. That would be a problem. Now let's get into the high-level design, and in this case let's actually start with kind of the data model and how we're going to be storing the data. We know, of course, we're going to be storing 2 things: the actual files themselves, and then probably a lot of metadata, things like user metadata, as well as metadata about these files. Now, because these files could be anything, if it's just a text file like a string, technically we could store that in a database if we wanted to, like a relational database or a NoSQL database. But we could obviously be having images, videos, like pretty much any format of file, so we need something much more flexible than that. Now, the metadata, of course, can just go in a database, whether it's SQL or NoSQL, probably doesn't matter. I would probably just go with NoSQL because it's going to be pretty straightforward. We're probably not going to be needing a lot of joins. It's going to be mainly, a key value store. That's how we're going to be using it. So, this could be something like MongoDB or AWS DynamoDB. But mainly, this is probably not going to be the bottleneck. We know we're going to be storing massive amounts of data, and that massive amount of data is probably not going to be stored here. It's not going to be the metadata. It's going to be the files itself. So how do we want to store these files? We're probably not going to be using like a regular database, but we do need this data to be persistent. So the two options that might come to mind for you is a distributed file system, something like Hadoop distributed file system, and another option would be an object store. Now let's briefly compare these two. I think they're both viable options as long as you can kind of defend your design decisions, but this is kind of one of the major decisions when it comes to Google Drive, of course, how we're actually storing the files. Now let's briefly compare a file system to an object store. First of all, a file system, just like on your local computer, is stored in a hierarchy. So going back to data structures and algorithms, which, believe it or not, don't go away, a file system can be kind of thought as a tree, not necessarily a binary tree, because you can have a folder, like let's say this is your root folder, and then here you can have some other folders like ABC, and maybe this is where your binaries are stored, bin, and some others. And then inside of these, maybe you do have some files like x.txt and things like that. And here we actually have another folder, and that can have some files in it as well. Basically, file systems store things in a hierarchy, and you can kind of visualize them like that, but in reality, they're also stored similar to this on your actual disk. Like on your computer, you have some persistent storage. That data is stored, organized in such a way like this, where if you're in a folder, you can go through all of its children pretty easily. It's well organized. And since Google Drive supports folders, you would think that this hierarchy is going to be helpful, which it would be. And one problem would be actually scaling this file system. Like I said, we could use a distributed file system where we have multiple nodes kind of storing all that information, and we scale it. Now this can definitely be much more complicated. That's kind of the downside compared to an object store, and it's less scalable. And with an object store, the scalability comes kind of for free, especially if we use like an external service like AWS S3 or Google Cloud Storage or Azure, which I think has Blob Store. Now, another benefit of a file system is that you can actually modify files. Like you can actually edit a file. You can't really do that in an object store. Files are immutable. You can delete a file and then create a new one, but you can't really edit an existing file. But since we're not really focusing on editing files, that won't be super important for us to actually like go in depth into. And there are, potential workarounds, especially if we were talking about small like text-based files. You could just kind of load the file and then kind of store it in memory somewhere and then edit it like that. You don't actually have to edit the file on the object store. And if it's something like a video or an image, maybe we wouldn't even support editing it in the first place. Now, just to kind of briefly wrap this up, an object store is more of a flat data structure. Even though in AWS S3 you can have folders, those folders are actually an illusion. They are just in the name. So like you could have some files like in my bin directory, I have some file like A, and then in the same directory bin, I have a file called B. If you opened up the bin folder in AWS S3 or something, you'd see these two files. You'd see the file A and you'd see the file B, but those folders are actually just in the name. Like the way that kind of logic works is it just sees, well, every file that has a prefix like the bin, I'm going to show all of those files now once you kind of click that directory. But in reality, these are stored in a flat data structure. There's no hierarchy. It can kind of be thought as a hash map where the ID or kind of the unique name of every file is like the identifier. And then when you use that name, you kind of see the individual file. You can download the individual file. So we will be going with an object store. Not to mention object stores kind of provide that reliability and availability for us, like multi-region replication and availability and all that stuff. So at a high level, we will have application servers. So if a user uploads a file, they will hit the application server. Of course, we could load balance this. It wouldn't really matter which application server the user hit, because ultimately the application server is going to just upload the file and store it in an object store. Now, as a file is uploaded, we also need to kind of store metadata about that file. Like we need to definitely have a reference to that file, because when a user now wants to read a file, they'll be hitting the application server. We'll be reading which file they wanted to read. We'll get the metadata for it, and we'll return like the actual file itself from object store to the user. And we would most likely just need a regular KV store. Something like a NoSQL database would probably work. Now, we can definitely have a caching layer as well. I mean, why not? But most likely, it's not like there's going to be a single file that's going to have that many reads. So caching isn't really the most significant part of this architecture, at least in the context of this problem. Now let's start going over some of the details. I mean, the good thing is at a high level, this is pretty straightforward, but there's a lot of details we could possibly discuss. One of the first things is typically in object storage, we've talked about like media files like images and videos, and generally you don't really need permission control on those, especially if you're going to be distributing them over like a CDN network. In this case, since these are kind of personal files that people are storing, they expect that only they will have access to them. And even though we're not talking about like sharing files and permissions, I think it's worth mentioning that you can kind of configure an object store to not be accessible publicly. directly. Like typically a user's browser would be making the request for like an image that's stored on an object store, which is maybe, so if a user is trying to access a file, our app server will be able to determine if they have access to it in the first place, probably using like our KV store, some authentication token from the user, and only then would it directly read the file and then respond with the file. Now, the storage, what it does is as a user uploads a file, that file is actually broken up into these blocks, and the block size is typically fixed. It could be on the order of like megabytes. Something like 4 megabytes might be reasonable. So every file is going to be broken up into 4 megabyte chunks, and those chunks are going to be stored in object storage. And so when a user now wants to actually read that same file, we have to reassemble it using these smaller blocks. And how we would know to reassemble it and how to do so would probably be based on data that we're storing in our KV store. So we could have a document in here saying that this is my file name ABC, and it belongs to this particular user. So we'd have like a user ID, and then we'd have like the references to all of the blocks, and then we could reassemble an individual file using all of those blocks. Now, why are we doing it this way? Well, one advantage to this, and the biggest one that I wanted to point out, is that if we break data up into smaller blocks, it's possible for us to do something called deduplication. That means, for example, for an individual user, if they're uploading multiple files and we're breaking every file up into blocks, but we notice that for one file, one of the blocks is identical to another file's block as well. And since when a user fetches a file, all we really need to do is reassemble that file. So if we ever notice any duplicate blocks for a single user, we will not store that. So maybe this is a file that a user is trying to upload, but we see that this block has already actually been stored in our object store, and we have a reference to it, so we would not restore this data. Maybe it would save us like 4 megabytes in this example, but on like a higher scale, this would probably save us more data if some users are duplicating a lot of data. Now, what would be even better is instead of doing this on a user level, we could do this on a global level for every single user. That means if I'm uploading a file that somebody else has already uploaded to Google Drive, we don't really need to store the exact same file multiple times, and also we don't need to store the same block multiple times. Eat a lot of storage. We probably delete referenced by another user's file, kind of a B for every single. Now that block is only being stored one time. It's the same block in an ID, like the actual use. This is probably how we would want to store a reference to every block in our KV store and intent of something, but then you edit on why. And if somebody is uploading a file and then that upload kind of messes up halfway through, like, you were uploading 10 gigabytes, but only 5 gigabytes were uploaded, and then you try to upload the next 5 gigabytes. Well, the good thing is, since we're, breaking everything up into blocks, we would notice that those first 5 gigabytes are already uploaded. We would not need to restore those in our object store in object storage, or alternatively, we don't actually have to store them here at all because they don't really take up any like data blocks or anything like that. We can kind of just store the metadata for all our folders in the KV store, and that's probably what I would prefer. So we can have that hierarchy in our KV store. We can, for every single folder, have a reference to all of its children, and of course every folder is going to be owned by a user. Like, there's no data blocks or deduplication in terms of folders or anything like that, and every folder would have like a reference, build those individual, kind of having two-way pointers, a pointer from the folder to the file and from the file to the folder. And we can have nested folders as well. Having pointers, I think, kind of addresses this problem. And another thing, I mentioned that when a file is deleted from object store, we actually never delete the data blocks from the object store because technically they could still be referenced by some other users. And for us, as a file, doesn't run like synchronously every time a request and then delete all of those being read. Would have like a load balancer here, most likely user traffic there. Data store, a DB, but whereas Zookeeper is more commonly used to coordinate distributed systems, it's highly available, it's highly fault tolerant, and it's a specialized solution for using heartbeats and coordinating a lot of distributed systems, including Hadoop, Spark, Kafka. I would be reading down, we handle that with design. So now let's design Google Maps or a similar service like Bing Maps or Apple Maps. So first, let's start with the background of what this is. You've most likely used a similar service like this before, maybe without even realizing it, because most apps like Uber and Lyft use internally a service like Google Maps.